We present SAMBLE, shape-specific point cloud sampling for an optimal trade-off between local detail and global uniformity. In our former work of apes, an attention-based sampling method was proposed for downstream task-oriented point cloud sampling. Apes discovers that sampling more edge points improves the performance of downstream tasks. However, this can be overdone, and selecting only edge points can be detrimental. For example, in few-point sampling, apes focuses excessively on sharpest regions and performs badly when the preprocessing operation is not performed. In this paper, we propose SAMBLE, which successfully strikes a better trade-off between sampling local details and preserving shape global uniformity. Moreover, input adaptability is achieved by learning shape-specific sampling strategies. The overall pipeline of SAMBLE is as follows. First, a sparse attention map is constructed and point-wise sampling scores are computed. Based on the point scores, bin boundaries are learned to partition points into bins. Afterwards, importance weights are learned for each bin using additional bin tokens to determine the bin sampling ratios. Finally, in-bin sampling is performed to yield the final output. The concept of sparse attention map originates from rethinking the mathematical characteristics of local details within point cloud shapes. One simple yet crucial observation was made: the frequency of each point being selected as a neighbor exhibits variation across a single point cloud. Building on this observation, we propose a sparse attention map to introduce new indexing modes. The sparse attention map integrates knowledge from both local and global information. 7 indexing modes are proposed and investigated. In the last two presented modes, NO stands for the number of selected cells in auth column, which is exactly the aforementioned, the frequency of each point being selected as a neighbor. To analyze the behavior of each indexing mode, we train a separate model for each mode, and visualize their sampling score distributions as heat maps. Considering the local-global trade-off, we chose the last indexing mode as the primary indexing mode for most of our experiments. For the part of bin-based learning method, the sampling strategy can be described by the bin partitioning process and the assignment of importance weights to each bin. First, we partition points into bins based on their sampling scores. To increase the model's input adaptability, we use unequal partitioning, and update the bin boundary values in a momentum-based manner. The next step is to learn sampling weights for each bin. Inspired by other methods that also used additional tokens, like BERT and VIT, we introduce additional bin tokens specifically for learning bin sampling weights. Bin tokens are initially concatenated with the input pointwise features for key and value. Subsequently, the combined features are subjected to a cross-attention with the original pointwise features, which is query. Afterwards, the attention map is split into two parts of a point-to-point subattention map and a point-to-token subattention map. For the point-to-point subattention map, the method introduced before is applied to obtain point-wise sampling scores and to learn the boundary values for bin partitioning. For the point-to-token subattention map, a mask operation is performed based on the partition result, and the sampling weights for each bin are computed with this equation. The final step is to perform sampling within each bin. Now we have the number of points and the sampling weights for each bin. Subsequently, the number of points to be sampled within each bin can be determined by scaling the weights. To avoid the actual sampled point number surpassing the available point number in one bin, a redistribution method is introduced. Within each bin, we adopt Boltzmann sampling. In this way, shape-specific sampling strategies are successfully learned for different shapes. Here, we provide a more intuitive comparison of different sampling policies. Top-M sampling selects points with the highest scores, while the bin-based method allows the inclusion of lower-scoring points if the model deems them beneficial for downstream tasks. Now we present the experimental results of SAMBLE. Please pay attention to the chair back and seat, the lamp shade, and the plant leaves. Compared to apes, we can clearly observe that SAMBLE successfully achieves a better trade-off in sampling edge points and preserving global uniformity. This conclusion is clearer with the model trained with the segmentation task. Again, please pay attention to the chair back and seat. The results for few-point sampling is more intuitive. Please pay attention to the last two columns in this figure. When pre-processing is not performed, apes can only sample the sharpest regions, while SAMBLE can achieve much better results even when only few points are sampled. This is because SAMBLE preserves better global uniformity. Here we present the shape-specific sampling strategies learned for chair objects. We can observe that analogous shapes within the same category exhibit similar bin partition results and learn similar sampling strategies. Here are more results of objects from other categories. From it, we can observe that shapes from different categories can learn distinct sampling strategies. Overall, our method successfully learns shape-specific sampling strategies for point clouds. To conclude, a novel point cloud sampling method, SAMBLE, is proposed in this paper by using a sparse attention map and bin-based sampling. It successfully achieves a better trade-off between local detail and global uniformity during the sampling process. For future directions, it is possible to extend the proposed method to point cloud scenes or even other 3D data representations, such as 3D Gaussian splatting. Thanks for watching.